Hi, I'm Antonio Sala, and in this video we are going to design a full proportional integral derivative PID controller for a double integrator process. In previous videos we have designed PD controllers, we have even designed PIDs by trial and error, we have discussed steady-state error and stability issues, but okay, in here, as a last problem in this case study, we will be given some specifications and then we will do model-based design of a PID controller to meet them. For a mass of half a kilogram, in which I assume I can exert a manipulated force, whichever force I wish, so I will compute the force from measurements, that's closed-loop control, and I will assume that friction is negligible, or if it is not, that with my measurements and my friction model I can compensate for it by some functions of the speed and Coulomb friction or whatever, so I can exert, apart from the force that my PID will compute, I assume I can exert a force that compensates friction, then okay, in that case my process transfer function is roughly 2 divided by s squared, so I wish to have a nice performance in set point tracking, say when my system is stopped at position 0, I wish to tell it to go to position 1 in a suitably fast way, let's say. And I also wish to have a sensible performance for disturbance rejection tasks, in the sense that if some wind or some slope in this platform makes a disturbance force appear, then I wish that my system does not move, or if it moves from sudden wind, it returns to the target position. So this will be my problem statement. Which will be the actual specifications? Well, I will solve my problem to achieve 0 steady-state error, position error, when subject to a step reference change. So I wish to go from here to here and end up at exactly the prescribed position. And also I wish 0 error when step disturbance appears. So if suddenly somebody changed the inclination of this platform, then I wish my system to react and keep my mass at the right place with 0 error to disturbances. These are static specifications, what must happen when the exponential transient has ended, and I also have dynamic specifications, which are those regarding the transient, and I wish a settling time of less than 2.5 seconds, let's say, with a non-oscillatory behavior. So this is our problem statement, and then we need to solve it. Let's go. In previous videos, and well, in textbooks as well, you can easily check that the closed-loop transfer functions from set point and input disturbance to error are 1 over 1 plus gk in set point case and minus g over 1 plus gk in the disturbance ejection case. So this will be my transfer function j and my controller k of s. For convenience, it will be this pink parameterization. This is a PID. We will use the pink parameterization in design because, well, maybe you are used to see the PID as in this blue parameterization. This is in fact the ideal form in Matlab, the one we will use in my simulation application. And okay, it's just dividing by S and extracting Kp as a common factor. And so this is the global control gain responsible for the overall proportional part plus some number times 1 over S, which is the integral action, plus some number Td times S, which is the derivative action. So apart from noise filter that we will need to put in my simulation, we will assume in theory that we have this blue controller parameterization, or well, in fact, it is equivalent to this pink parameterization that we will use next. So I leave to you as an exercise to replace g and k in here, and as g times k has s cubed in the denominator, you should multiply everything by s cube to remove denominators and reach this nice and pretty expression for the closed loop error transfer functions. So we need to analyze if we can meet our required specifications. And first, will we be able to stabilize the system? Indeed, we will, because we have what I call total controllability, in the sense that look at the denominators. Each of the three design variables, ki, bar, kp, kd, are appearing at a separate polynomial coefficient. So, well, by suitably choosing these three constants, we can set the denominator of the transfer function to whatever desired denominator we wish. So indeed, we will set it to be stable polynomial in a minute. So no problem with stabilization with dynamics. We are lucky. And regarding then steady state performance, steady state tracking error, well, we would need to use the final value theorem, but okay, the basic conclusion of that is that if we get, for instance, this transfer function and we replace the Laplace variable by 0, then we get the DC gain, which is 0, and that means that when subject to a constant input, the output error will be the constant input times the DC gain, so the error will be 0 when subject to a constant du force disturbance. Good. And likewise in here, if I set S to 0, again, this 0 DC gain will ensure that the error will be 0 when subject to constant step setpoint changes. So good, we can meet our static specification and we can stabilize, so this is good news. The thing is, why do we need a PID? Well, because if we recall previous videos, with no integral action, I had 0 setpoint tracking error, but I did not have 0 disturbance rejection error, so I need a PID. And indeed, for instance, if I had just a PD regulator, this S will not be here, so the DC gain of this thing will not be 0. So I need integral action to have this S here, and then I can reject the step input disturbances, because, okay, an alternative way of seeing that is that this is a derivator, so if my input is a constant, once the initial condition, whatever transient, ends, the derivative of a constant will be 0. And indeed, this S cube is a triple derivator, which means that when subject to references in the form a plus bx plus cx squared, the third derivative of this will be 0, so I will have 0 steady state error when exponentials finish. In reference tracking, not only for constant, this a, let's say, set points, but also for ramp and parabola, so that would be the super good steady state behavior of set point tracking in this case, at least in theory. So good. We are then happy with our steady state error behavior, 0 error with step disturbance and set point, and then the only remaining bit is delving into the stabilization and pole placement methodology, in the sense that, okay, as we had total controllability and this denominator can be made equal to whatever denominator I wish, well, which is the denominator I do wish? Okay, if my settling time is 2.5 seconds, then a first order formula for an exponential tells me that settling time is 3 over the real part, the 95% criterion, if you remember, or again that the real part of my pole must be negative, of course, more negative than 3 over desired settling time. So in this case, 3 over 2.5 is 1.2, then if the real part of my poles is minus 1.2 or minus 1.5 or minus 2 or minus 20, then the poles will be fast enough to meet my settling time criterion. But, okay, just be aware that this 3 over settling time comes from a first order formula, and this system is third order. We have here a cube. So maybe when we simulate things will be a bit slower than expected because we have 3 poles instead of 1. That issues are not usually considered in first courses, in which, okay, you apply the first order formula and then you can fine tune later on, as we will do later on. Okay, well, the thing is that we wished this real part of my poles and I was requested to have a non-oscillatory transient, so all poles must be real. So we will set 3 poles at minus 1.2, and then this means that this thing will be my desired polynomial, and if I equate my denominator to the desired polynomial, well, carrying out operations, s plus 1.2 cube is this thing, and so 3.6 will be 2kd, 4.32 will be 2kp, and 1.73 will be 2ki. So with this, dividing these numbers by 2, I will get the required controller and my exam problem will be finished. As we are now in Matlab, then we will do some simulations to check that indeed the specifications are met. So if we go back to Matlab, I used symbolic toolbox to just compute the polynomial I wished, and then these coefficients divided by 2. 3.6 divided by 2 is the derivative gain, 4.32 divided by 2 is proportional, and 1.728 divided by 2 is k-integral bar, because in here this was k-integral bar, and I call this k-integral without bar, it's just notation. So this is the closed loop controller. This is my pink parameterization of the controller we discussed here. And then the feedback command of Matlab computes the closed loop transfer function from setpoint to output. I mean, we worked with the error in our theoretical derivations, but what we will see in an experiment, let's say, is the output, the mass moving, so I will simulate the output. But we worked to make the error small in a fast way, but okay, simulations will see the output. Well, this is the feedback setpoint to output transfer function, and indeed if I compute the poles and zeros, we do see that the poles, the denominator, is the polynomial we wished, 3 poles in 1.2, and then, okay, we have some stuff in the numerator, but as we are applying a pole assignment methodology, we can do nothing with respect to what happens in the numerator, in the sense that once we decide the poles, then we get the PID constants, and then that constants somehow appear in the numerator of the output transfer function, but our methodology does not allow us to do anything about it. If you know 2 degrees of freedom control, whatever, then you will be able to do something, but this is not the case with the theory we have used. So we are happy with the denominator, and then we just don't look at the numerator and just simulate step response. Then the step response, with also a 5% error bar around the set point, ends up being this. We see that indeed in 2.5 seconds we are lucky and things get into the 5% error band, and it finally ends at 1, which is the desired set point. So this is a nice result. And also we have, in theory, real poles, non-oscillatory behavior. As we have a couple of zeros in the numerator, then, okay, strange things happen with overshoot, whatever, because of the numerator terms. So this is a non-oscillatory transient, but okay, it seems sort of oscillatory. Well, that's the effect of this numerator we are not allowed to analyze. And also we don't wish to, it's kind of, we'll fine-tune that later on with trial and error simulations. So once we are supposedly happy with the set point tracking response, then this is how I compute this transfer function g over 1 plus gk, this syntax of the feedback command. So this is 2s over the desired denominator, indeed in accordance with this theoretical development, 2s over my denominator. Here we have it. And then if I plot the step response, here I have the step response that, okay, it ends up in 0. So if I have a constant wind, my integral action will react and place again my mass at the exact desired position. But well, regarding settling time, okay, I would rather say that settling time is 6 seconds and not 2.5. So what is happening is that in here we are sort of seeing that 3 real poles may have a slower transient than the one I compute with the formula for a single exponential, because in here we have 3 of them. But okay, let us imagine that we are happy with this, so we will give our design as finished. Then this will be the solution to your theory exam. But now we are going to discuss the theory-practice gap. First, I will compute the blue parameterization to simulate in my application by just dividing by KP. So these are the numbers that I will put as overall controller gain, integral inside the parentheses, and derivative time inside the parentheses. So these 2.16, 0.4, and 0.833 are the things that I have placed in my PID simulation. I disabled measurement noise and saturation, and also I disabled the derivative noise filter, because filtering at 1000 radians per second is kind of infinite frequency for things that take 5 seconds to go up and down. So this is, in fact, just a copy of what the stat command did output, in the sense that, okay, this set point tracking fragment of the response will be just a copy of this with changed graphical scales. And again, the disturbance rejection step response, this one, well, this is a unit disturbance plus 1, and in my application I was simulating minus 0.6, so with suitable scaling and turning it upside down, this plot is identical to this part of the plot in my simulation. So for the moment being, I've done nothing compared to what I did in Matlab. But now let us turn it to a more realistic simulation by introducing measurement noise. In here, we need noise filtering for sure, otherwise my actuator will not be able to do this rubbish manipulate force. This is pure random. And if I turn on saturation, then things cannot go up so fast. And the theoretical response is very different from the practical one. So what is happening? Well, in order to fine-tune my theoretically designed regulator to work in practice, I need a noise filter. So I filter, let's say, at 7 radians per second. So signals are somehow much cleaner, or even I can filter a little bit more, 4 radians per second. Good. And the second thing is that regarding saturation, well, this initial part of my cyan theoretical line with no saturation is due to the fact that the PID I designed, the set point derivative is infinity. So we have a so-called derivative kick that will go to infinity, but after filtering, okay, it goes to 7 or 8. But my real actuator can exert only a force of 1, so it starts going up like 8 times slower. In fact, if I tell my derivative action to disregard the derivative of the set point to avoid derivative kick, then with this c equals 0, it's the so-called 2 degree of freedom output only derivative. We did not discuss the equations of this in the theory, but as a practical refinement, okay, then if we assume that that infinite derivative kick from the step set point will never happen, so we don't even let it happen in the equations, well then, in this case the cyan line and the dark blue one without saturation, they are much closer. And again, also if because of saturation I accumulate too much error, I need to apply the so-called anti-windup, so my final dark blue response will be the practical implementation with this output derivative, anti-windup and noise filtering that will possibly make it work in a realistic setup. So one thing is passing my examinations with a very high mark by doing these kind of operations, and another thing is deciding whether my requested specification are sensible for my particular masses and forces that I can exert, and fine-tuning my regulator with these kind of filters, anti-windup and to degree of freedom stuff, so that my theoretical solution is adapted to work in a practical application. But okay, this last fine-tuning and adaptation is not the subject of your first control courses, so if we go back to the no noise, no saturation, set point derivative, no filtering, then this is the theoretical result we solved and the one asked in your examinations in your first control theory course. So we finish with this. Thanks for watching.